Welcome to physics class on electromagnetic waves. Let's try to see what are the points to be discussed in this uh, video class. We need to discuss about the properties of electromagnetic waves, Hertz experiment, then electromagnetic spectrum, wavelength and frequency ranges, and the sources and uses of these different electromagnetic waves. But before going further electromagnetic waves, let's try to discuss about the different forms that will be coming up to give rise these electromagnetic waves. Now we can consider these different forms of equations. We can call it that as Maxwell's equations. There are four equations, okay? We may call it that as Maxwell's equations, and these equations more or less we have already discussed in the previous chapter, except one equation, the last equation I mean. The first equation is known as what your Gauss law in electrostatics. Gauss law may be of 2, and this is in the case of what electrostatics. Statics. So what does this Gauss law states? Gauss law states that the total electric flux, okay, that is denoted by phi, or we may call it that phi as what surface integral of E dot ds over the whole surface, okay, this is equal to 1 by epsilon naught times the charge that is enclosed by the closed surface. So we call it this as what Gauss law in electrostatics. So this law gives the value of electric flux in terms of charge enclosed by the closed surface, capital S. Got it? This equation gives an electric field due to the discrete charge or due to certain charge distribution, and tells that the electric line of force starts from the positive charge and ends at the negative charge. The electric line of force do not form a continuous closed path. This law predicts that isolated charge exists. We can have plus charge, negative charge, isolated. But that this is different in the case of what Gauss law in magnetostatics. Another law that is known as, this is similar to this Gauss law in electrostatics, and this Gauss law, this one is in the case of magnetostatics. As there is no isolated pole, or you can say monopole never exists, so we can write that the magnetic flux, which is equal to B dot ds, instead of electric field we are taking magnetic field, so we may call it this as magnetic flux. That means it is equal to what surface integral of what B dot ds. This will be equal to what, instead of that 1 by q, what it will be equal to what, there is no isolated charge, so as there is no no isolated pole exists, so this side, right side, will be equal to 0. So what happened, this gives that law known as Gauss law in electrostatics, and this shows that magnetic line of force entering a closed surface is equal to the number of magnetic line of force leaving it. There is no starting or no end point in the case of magnetic line of force. Thus, the magnetic line of force always forms closed paths. If it were not so, then isolated magnetic pole would have existed. Thus, this equation confirms the absence of monopole. So we say that no monopole exists, right? Like that. Got it? And Let's take it the third law, that is known as what your Faraday's laws of electromagnetic induction. The third one is known as what? Faraday's laws of electromagnetic induction. Let me call it as EM induction. Got it? Yes. The Faraday's laws of electromagnetic induction states that the rate of change of magnetic flux is directly proportional to the induced EMF, right? So taking into account that of the Lenz's law, we may write integration of E dot dl. This will be equal to minus, this is for the Lenz's law, d by dt of the what magnetic flux phi v. So instead of that phi v, let me write it for the time being as b dot ds. This is the magnetic flux over the whole surface. So this is nothing but it is just like that of your what induced EMF E is equal to minus d phi by dt. It is same thing with that one. Okay, this is known as Faraday's laws of electromagnetic induction, and this law gives a relation between electric and magnetic field. Electric and the magnetic field. Got it? Electric and magnetic field, or you can say electric field and a magnetic flux in one sense. This law shows that the line integral of electric field over any closed surface around a closed path, I should say, around a closed path, that is the induced EMF, is equal to the time rate of change of magnetic flux, okay, through the closed surface bounded by the closed path. Got it? And the last one is known as what? Modified Ampere's law, or we may call it this as the Maxwell's, okay, Maxwell's law, because it is just like that of the Ampere circuital law, but it has been modified by Maxwell, and this has been named as Maxwell's law. And in this, what happened, the equation is that there is a relation between the magnetic field and the current. Okay, so this magnetic flux, okay, over this closed part, this will be equal to mu naught times the conduction current. This is equal to mu naught times the displacement current. What is this displacement current? Displacement current is that current which exists whenever there is a time rate change of electric field. Wherever there is a conduction current, displacement current will not be there. Wherever displacement current is there, conduction current will not be there. That means both are what one of the same part. Okay, if conduction current is there, displacement current will not be there. If displacement current is there, conduction current will not be there. Okay, just to have the continuity, say for example in the case of a circuit containing a parallel plate capacitor, through the connecting wire conduction current will be there, but in between the two plates of a parallel plate capacitor there is change of electric field, and if there is a change of electric field, that means time rate change of electric field, then in between the two plates similar or equivalent, okay, current equivalent to the conduction current is flowing, and that current we call it as what? The displacement current. So it happens whenever there is what? The change of what? Electric field with time. So it will be equal to mu naught epsilon naught d by dt of this displacement current is what? D by dt of the integral of E dot ds. E dot ds. This part is nothing but this is the electric flux part. Got it? electric flux part, that means rate of change of electric field with time. Okay, so this is the last equation, and this equation is known as what? Ampere's Maxwell law. This law states that the line integral of the magnetic field, okay, the line integral of the magnetic field around any closed path is related to the conduction current and the displacement current. Conduction current and the displacement current. This law predicts that the magnetic field can be produced by a conduction current as well as by the displacement current. You can call it that conduction current can also give rise to the magnetic field, and moreover this time rate change of electric field may also give rise to the magnetic field. Okay, so these are the laws that will be required for the discussion of these electromagnetic waves. Now let's see. Okay, let me erase it out and then let's see. Now for a region where there are no charge and conduction current, Faraday's and Ampere's law takes the symmetric form. The first one is nothing but this is your that one Faraday's law. Okay, that the induced EMF is what? Directly proportional to the rate of change of magnetic flux, and this one is what? Your this the second one will be what? Your this one is Ampere's modified, okay, circuital Ampere Maxwell's law, I should say. Now it can also be shown that the time varying electric field produce space varying magnetic field, and time varying magnetic field produce space varying electric field. Okay, that means both are what? Contrary. That means if one is varying with time, it will give you the other one. That means whenever there is a time varying electric field, it will produce what? Space varying magnetic field. Whenever there is a time varying magnetic field, okay, on the other hand, whenever there is a time varying magnetic field, it will produce what? Space varying electric field. The equation is also given here. Got it? These are the equations. I'm telling you that this one, see, this is the what? Time varying magnetic field. This J, okay, here these are nothing but these are the mathematical operator. Okay, you can take it for the time being as you have not learned, but you will learn it in higher classes, okay, in mathematics. So now this time varying, that means Bz is the magnetic field, and this B is along the z axis, that is represented by Bz. Okay, magnetic field that is varying with time along z axis, that is denoted by Bz. Okay, so what happened? This what? Time varying magnetic field will produce what? Time varying magnetic field will produce space varying X. See, space varying electric field. Now this time varying magnetic field along z axis, okay, it will produce space varying electric field along y axis. See, y is there, EY. Got it? So what happened? This time varying magnetic field will produce what? Space varying electric field, and on the other hand, time varying what? Electric field will produce what? Space varying magnetic field. But when you see these two, that means this electric and magnetic field, they are perpendicular to each other. Got it? Now let's see that electric and magnetic field are produced or they can be produced by one or the other. Okay, that means electric field and magnetic field are sourced to each other. Electromagnetic wave is a wave in which electric and magnetic field are perpendicular to each other and also perpendicular to the direction of propagation of the wave. Now let's see about the properties of electromagnetic waves. Okay, now just to know that, let's try to have this picture. Okay, let's take it that this is along x-axis, okay, and y-axis, z-axis, like this. Okay, if there is an electric field, okay, lying onto this xy plane, that means if it is lying on the xy plane, means what? It is perpendicular to x-axis. Okay, now see this wave, this the yellow or the white wave is the electric field, and this red wave is the magnetic field. That means electric field is varying, okay, with time along what x-axis, that means xy plane, I should say, along xy plane. And whereas your magnetic field, that is the red wave, it is varying with what, the xz plane. So both are varying, and the wave is going along the x-axis. One is varying in the xy plane, red wave, which will represent the magnetic field, that is varying along xz plane. But what happened, your electromagnetic wave, that is propagating perpendicular both to it. That means it will be perpendicular to the what, xz plane, I mean xy plane. Okay, perpendicular to yz, I should say yz. This is the yz plane. This plane is the yz plane. So perpendicular to it, electromagnetic waves will be propagating like this along x-axis. So what happened, this is the electric field. Okay, electric field is varying here, got it, like this. That means what, electric field is varying in the yx plane. Okay, in this plane it is varying, got it. You can make it this plane as the xy plane. So electric field is varying with time, okay, onto this xy plane. And your magnetic field is varying, magnetic field is varying along this plane. This is the plane which is known as what, xz plane. X here, z here. Okay, so your magnetic field is varying here like this, in this plane itself, got it. So as your magnetic field is varying with time along this what, xz plane, at the same time, what happened, your electromagnetic waves will be vibrating perpendicular to this. That means along this plane, you can say. That means your magnetic field will be perpendicular to both x as well as z, and it will be moving along the x-axis like this. So what happened, let's see the propagating nature of these what, electromagnetic waves. Now if you see this, then it will be like this. See, it is propagating along x-axis, right? Have you seen? Yes, no? So the peak value of the electric field is denoted by E naught, and the peak value of the magnetic field, it is denoted by what, B naught. Let's see, this is the E naught. See, somewhere here is the E naught, okay, and for the magnetic field it will be also along the z-axis. Have you seen that B naught there? So the variation, okay, in both the electric and magnetic field occurs simultaneously. Therefore they attain their peak or maximum value at the same place and at the same time. Got it? These are the properties. Okay, we have started the property. Number 2, the direction of electric and magnetic field are mutually perpendicular to each other, and as well as perpendicular to the direction of propagation of wave. The wave is propagating along what, x-axis, electric field is varying along y-axis, and the magnetic field is varying what, along z-axis. So electric is along x-axis, magnetic field is along z-axis, whereas the electromagnetic wave is propagating along x-axis. Now if this electromagnetic wave or electric and magnetic field, if they are varying perpendicular to each other in vacuum, then the electric field vector and the magnetic field vector are related with the speed of light in vacuum. That is, c is equal to, where c is nothing but this is the speed of light in vacuum. Okay, this c is related as E naught by B naught. So after knowing this maximum value of this E naught and this B naught, okay, we can relate the speed of electromagnetic wave c as what? C as E naught divided by B naught, the ratio of the peak value of electric field and the magnetic field that will give you the speed of light. Rather, the speed of electromagnetic wave that will be traveling or propagating will be equal to the ratio of the peak value of electric field and the magnetic field. Got it? Had it been not in the vacuum, had it been in some other medium having having permeability mu and what that absolute permittivity epsilon naught, then the ratio would have been what? The speed, okay, the rather the two relation between this c and mu naught and epsilon naught will be expressed as c is equal to 1 by under root of mu naught epsilon naught. Okay, this is for the that of what? The speed of light in terms of that of what? Mu naught and epsilon naught. As I told you that had it been in some other medium, then instead of this epsilon naught and mu naught, it would have been if mu and epsilon only. Okay, and that mu and epsilon are nothing but they are the permittivity of the medium and permeability of the medium and permittivity of the medium. This mu naught, instead of this mu naught, it will be coming as what? Mu, and instead of epsilon naught, it will be coming as epsilon. Okay, epsilon only. What are these mu and epsilon? That are nothing but that will be equal to what? Mu is nothing that the absolute permeability of the medium, and epsilon is nothing but that is absolute permittivity of the medium. As I told you that this velocity, okay, in that, if it is in the vacuum medium, then it would have been what? Your epsilon naught, E naught divided by C naught, B naught, B naught, and this can be related as what? 1 by of what? Mu naught epsilon naught. Okay, these are nothing but these are the permeability. Mu naught is a permeability and your epsilon naught is nothing but this is the permittivity of free space. Okay, but had it been in some other medium, okay, having what? The absolute permeability mu, okay, and the absolute permittivity of the medium epsilon, then your c would have been related as what? 1 by root over of mu epsilon. That is the meaning that I want to convey. Okay, so let's see in the next part. It will be coming up as like this: the velocity of electromagnetic waves in a material medium. That is what I said, if it is in the material medium other than that vacuum, then your c would have been related as 1 by root over of mu epsilon, where mu and epsilon are what? Absolute permeability and absolute permittivity of the material medium. Now, as this electromagnetic wave is a wave, so what happened? It should obey that of the principle of superposition. Got it? Now, electromagnetic waves carry energy as they propagate through space. Okay, we know that when wave is propagating, it always what? Possesses that energy while it is in propagation. Okay, so likewise electromagnetic wave also carry energy as they propagate through space. The energy is divided equally between the electric and the magnetic field perpendicular to each other. Okay, Electromagnetic waves can transfer energy as well as momentum to the object placed on their path. This we have already learned in the lower class, that whenever any wave is propagating, then what happen, it transfer energy as well as momentum. Okay, and next one is for discussion of optical or effects of electromagnetic waves, what happened, more significance is given to that of the electric field vector E. Therefore your electric field is called the light vector, so as to have that of polarization. Your light is a transverse wave, so the transverse nature comes from this electric field, variation of this electric field with time. So we call it that electric field as light vectors. Got it? So whenever one asks you why this light is a transverse wave, or why this propagation, polarization, not propagation, polarization is possible in the case of light waves, then you have to say that the electric and magnetic field are perpendicular to each other, and moreover this electric and magnetic field are propagating perpendicular to electric as well as magnetic field. And this perpendicular nature of these light waves, it comes from that of electric field, and so this electric field vector is known as light vectors. Okay, so polarization is possible only because of this electric field. Got it? Now let's see the next part. Your electromagnetic waves does not require any material medium to travel. Okay, as it is not the material wave, rather this is electromagnetic waves. If it is electromagnetic waves, then it will not require any material medium for its propagation. It can propagate in space, no doubt it can propagate in medium also, but if there had been no medium at all also, electromagnetic waves can propagate, unlike that of material waves. For material waves, like that of water waves, sound waves, we require a medium for its propagation. But for electromagnetic waves, no medium is required for its propagation. That is why light, okay, sunlight, let's take it, sunlight from the sun up to the earth, where there is no medium in between these two heavenly objects, still light can travel from sun and it can reach up to the earth surface, right? And the source of these electromagnetic waves is nothing but this is the the oscillating charge. So oscillating charge is the source of electromagnetic waves. Okay, now let's see about the Hertz experiment. Actually this Hertz experiment, I think it has been deleted from your syllabus, but still just to know how electromagnetic waves are produced, let me give you this brief explanation. I will try to move very quickly. Okay, now let's see that these are the two copper or zinc plate, okay, which are placed around 60 centimeter apart, and these two are connected with the rods. Okay, and these two rods, onto this rod there are two steel or spherical balls placed over it, and it can slide over this rod. Okay, that means just to make the different distance of separation between these two spherical metal spheres, okay, S1 and S2, you can slide this sphere over here, okay, like this. It can slide up and down like this through this rod. Okay, and in the actual experiment it is placed about 2 to 3 centimeter apart. Okay, and these two connecting rod or metal rod, it is connected to the induction coil, so as to provide a high voltage of around, say, of thousands of volts. Okay, and now what happened when this induction coil is connected to this sphere, then what happened, electromagnetic, okay, waves will be produced. How it will produce, as the gap is less, and what happen, your discharging of the charge will take place in between these two spheres, S1 and S2. Okay, in between this there will be discharging takes place, due to the oscillations of the charge, what happened, as this is the induction current, that means the current coming here will be what, AC in nature. So as the charge is going to oscillate about these two spheres, then what happened, discharging will take place and electromagnetic will start propagating perpendicular to it. So your electric field is perpendicular, uh, that means onto the plane, not perpendicular, rather onto the plane of your screen, and magnetic field will be starting perpendicular to this plane. Okay, electric field will be either it will be from S1 to S2, from S1 to S2 like this, so it will be parallel to the plane. Okay, and around this electric field, what happened, magnetic field will be developed around it like this. Okay, it may be like this in this direction, or it may be like this, so it will be oscillating. The magnetic field will be also oscillating depending upon the direction of the electric field. So electric field and magnetic field are what, perpendicular to each other here. So perpendicular to it, what happened, electromagnetic waves will be propagating, and this is a source of what, your electromagnetic waves. But if you want to detect these electromagnetic waves, then Hertz kept a what, spherical, or like this, two spherical balls, similar two spherical balls here like this, S1 and S2. Two spherical balls will be placed here with a ring, okay, like this, connected with the two rings by a sphere. So the diameter of this ring will be around, say, 70 centimeter, or you can say 0.7 meter. And whenever that electromagnetic waves is coming, then similar sparks will be coming up, will be seen here in between the two spherical balls. That means this represents that electromagnetic waves are propagating. Okay, and it reaches up to the spherical ball. But mind you that such spark will only be coming, and it will be intense when the plane of these two spherical metals, it is are parallel with this one. That means when the gap is along in the plane like this, it must be also the gap here in the two spherical what metal. When these two gap is also same with that one here and here, then only what, sparks comes out. That coming of spark is nothing but that is the detection of what, the electromagnetic waves. So let's see about that phenomenon here. Let me show you. Okay, see, whenever there is a ring there, okay, with the two similar metal what, space, when placed at the two ends like this, of around say 0.7 meter, and whenever there is induction current that is passing through these two spherical metals S1 and S2, electromagnetic wave starts propagating perpendicular to the direction of magnetic field and electric field. And similarly, you can also see that the two metal spares in the ring also, it produces the spark similar to that in the case of S1 and S2. Okay, they are in S1 prime and S2 prime also, what that sparks comes out. That shows what, the detection of what, your electromagnetic wave. Electromagnetic wave, the first part is here, the first part is here. This is nothing but this is the production of electromagnetic waves. Okay, and this part is nothing but this is a detection of electromagnetic waves. That means the spark that is coming in between the two spheres S1 prime and S2 prime here, these two are nothing but the spark is due to the detection of electromagnetic waves. So likewise, what happened, you can also this Hertz was able to produce the electromagnetic waves, not only the production of electromagnetic waves, rather it can also detect electromagnetic waves. Okay, so let me give you a brief description about this, and I will try to switch on to the next slide. Okay, I will not take much time. Okay, but how this is produced, let me tell you. These, the two plates, okay, these two plates, this one, the first one, and this second one, this will act as what, the parallel plate, okay, of low capacitance C, and this the connecting wire or the connecting rod, this will act as the low inductance L. Okay, low inductance L. So it seems that there is what L and C connected it, and you must be remembering about that LC oscillation, right? So this electromagnetic wave will produce the frequency nu, and it will be expressed as 1 by 2 pi root over of LC or CL. Okay, this much amount of frequency it can be produced by these electromagnetic waves. So depending upon the value of L and C, you can have or produce the different frequency. Got it? So let's switch on to the next slide. Due to the high voltage, the air in the small gap between the space get ionized, and this provides the path of the discharge of the plate, and spark begins to produce in between the two space S1 and S2. Okay, likewise these are nothing but these are the descriptions of all those what that Hertz experiment, which will explain about the what production and detection of electromagnetic waves. Got it? So let's see about the spectrum of these electromagnetic waves, starting from the very what high a low frequency or very long waves, starting from the radio waves. Let's move on to these different spectrums of the electromagnetic wave: radio wave, microwave, infrared, then visible wave, then ultraviolet, X-ray, then goes to what gamma rays. Okay, so let's try to see these different forms of what electromagnetic wave, and these electromagnetic wave we call it as what electromagnetic spectrum. Now in this electromagnetic spectrum, as the syllabus has been reduced, and here you need to know this range of electromagnetic spectrum. Okay, in the increasing order of what frequency or in decreasing order of that wavelength. Okay, you need to know it, and you should know the source of this what electromagnetic wave, and at the same time you should know the uses also. Okay, which one is coming with the longest wave, then next, okay, it will keep on decreasing, and at the last what happened, your what gamma rays will have the least wavelength, and your radio wave is having the least frequency, whereas your gamma ray will have the longest what frequency, highest frequency I should say, not longest. Okay, so you need to know that radio wave, it is the range of wavelength, this range of lambda means range of wavelength, range of frequency. You need to know all these things, you need to remember it. Okay, in this chapter you will only be asked of this type only: what will be the range of frequency, range of wavelength, like that, and what is the source of this radio wave, and where can this particular electromagnetic wave be used. Those things can only be asked, okay, from this chapter. So I will not go in detail about this, rather you go through it by pausing it, okay, and then you will know it. But this is only some brief descriptive part only. Okay, I will not give you that elaborate one. You try to find it out from any book. About the microwave also, it can be used in rather analysis of fine detail of atom and molecular structure, and in microwave oven. Like this, there may be some another uses of microwave also. Okay, that microwave can also be used to clean the what dust. Okay, wherever that is hard to reach by our hand, it can be also used to clean such things. Okay, so such all details may not be here in the in my table. Okay, you please try to find it out from some other book also. The more you are having the different types of application or uses, then it will be easier for you to give answer in the examination. Okay, so these are about that of ultraviolet rays, then X-rays, then comes to your gamma rays. Okay, gamma rays has the least wavelength, and as your frequency and wavelength are inversely proportional, your gamma ray will have the highest frequency in this electromagnetic spectrum. So you need to remember those different spectrums coming from gamma rays, x-rays, ultraviolet, then visible radiation, that means BIPR, then goes to infrared, then goes to what, microwave, then radio wave, like that. So you need to remember all these the frequency ranges and the wavelength ranges, and moreover the source of these electromagnetic waves as well as their uses. Okay, with that we will try to end up with this. Okay, you try to pause the video and you try to note down, okay, those different wavelength range, frequency range, their sources and their uses. Okay, with that note we will try to come to the end of our today's class. Thank you.